In this video, we're going to look at another example of linear programming. So in this case, we've got a toy company that makes cars and trucks. So they're confident they can sell everything that they make, and each car needs 4 wheels and 2 seats, truck needs 6 wheels and 1 seat, and they have 360 wheels and 100 seats in stock. And we'll just say that this is their daily production. So profit on a toy car is $2.75. Profit on the truck is $1.50. So how many cars and trucks should they make in order to maximize profit? Well, I'm looking at my data and I see a car needs more seats, but a truck needs more wheels. We have far more wheels than seats available, but that makes sense because both the car and truck need a lot more wheels. And then the profit has toy cars making much more profit, which makes us think we should sell mostly or possibly all cars. So those are just some ideas I'm thinking of as I'm looking at these values here. Well, first we need to figure out what our variables are going to represent. So X and Y, we don't know how many cars we're going to sell and how many trucks we're going to sell. That's what we're trying to figure out what to do. So the two things that are unknown, the value could change each day, is the number of cars sold and the number of trucks sold. So we're going to do X is the number of cars that we sell each day, Y is the number of trucks we sell each day. So now we want to state the objective function, and that's what we're trying to maximize. Some cases we're trying to minimize something, but in this case, we're selling a product, we're trying to maximize that profit. Okay, so we look in our question here in the problem, and it tells us what we're trying to maximize. So we want to maximize profit, and our profit, and we can just take the first letter of whatever we're trying to maximize or minimize. So P, our total profit, is equal to 2.75x plus 1.50y, because that represents the profit for each car that's sold and the profit for each truck that's sold. Okay, so now we're going to take a look at our constraints, and then we have to graph them. So our constraints, right up here, the only other information we're given is the number of wheels and seats that our two toys need and how many that we have available. So I see a car needs 4 wheels and 2 seats, truck needs 6 wheels and 1 seat. So we got to think about, okay, are my constraints or my limitations, are they wrapped around the topic of a car and a truck, or a wheel and a seat? Well, the X and the Y represent the car and truck, right? And we also have to have a total with our numbers. So 360 and 100, those seem like the totals that we're going to use, and they have to do with wheels and seats. So our constraints are going to end up representing wheels and seats. So for wheels, if I can scroll down here, we've got 4x plus 6y is less than or equal to 360. So how I got that is I need 4 wheels for every car, which is x. So 4 times x, plus 6 wheels for every truck, and truck is represented by y. So 4 times x plus 6 times y, that represents how many wheels we use for every car and how many wheels we use for every truck. And we only have 360 wheels to use each day. So the amount that we use for the cars and the trucks must be less than or could be equal to 360. It can't be more because we don't have more than 360. That's our limitation, that's our constraint there. Our other constraint has to do with our seats. Our car has 2 seats, our truck has 1, and we have 100 seats total. So similar to our wheels constraint, we have 2 times x plus 1 times y must be less than or equal to 100. So now we have our constraints, but now I need to graph them. Now, I don't really want to solve these equation or inequalities into slope-intercept form, where I need to get y by itself. I think it's just going to be easier, at least for me, to graph my x and y intercepts and then connect those 2 points for my line. So for my x-intercept, my y value is 0, so I just basically cover up the y term. And now I solve as if it was an equation for x equals 360. So divide both sides by 4, and we get 90. Now for our y-intercept, our x value is going to be 0, so I basically cover that term up because 4 times 0 is 0, so it's like that x term isn't even there. And then 6y, I'll say, is equal to 360, because we want to know at that exact point what's the y value, so I make this an equal sign instead. Divide both sides by 6, and I get 60. So my x-intercept is 90, my y-intercept is 60, and I'm going to graph those 2 points. 90, 60. I want to be as accurate as possible because my constraints are going to intersect, and I need to know where those vertices are. Okay, so now with my second inequality, 2x plus 1y is less than or equal to 100. For my x-intercept, cover up my y term, and now I have 2x is equal to 100. Divide both sides by 2, I get x equals 50. And then for my y-intercept, my x value is 0, so I cover up my x term, and now 1y equals 100. Well, that's just y equals 100. So my y-intercept is going to be 100. So 50 for my x, 100 for my y, and then connect those 2 points. Okay, so now we need to look at our feasible region. So we've got our constraints drawn out. We also have to remember that we've got these common sense constraints with the x and y axis. So y is greater than or equal to 0 is represented right here, and x is greater than or equal to 0 is represented right here. Because in these linear programming examples, it's real-world situations, we're not going to sell negative cars. We're not going to sell negative trucks. We're only dealing with positive numbers. So basically, once we have our constraints drawn out, go from our origin in our x and y axis and just kind of go up and out until we meet our other constraints. So our feasible region is going to be right in here. A little out, but that's okay. And now I can see that I've got the vertex, well, technically at 0, 0, because it is where our constraints intersect along our feasible region. We've got a vertex right here at 0, 60, over here at what looks like 30, 40, and then out here at 50, 0. So we've got 4 vertices here, and we want to evaluate each of those vertices into our objective function and see which one maximizes our profit. Okay, so clearly the 0, 0 vertex in every situation that we look at is not gonna be the vertex that we want. It's gonna give us, in this case, 0 profit, so we don't even really need to evaluate that. So we're gonna look at these 3. Typically, the points that are on the x or y axis, where you're not even including one of the 2 variables in the situation, those aren't going to maximize or minimize whatever the situation is. So if I were to guess, I would say that this point is going to have the most profit. So once again, the point 0, 0, we substitute in for x and y here, but that just gives us a profit of 0. So we know that doesn't work. So then 0 cars and 60 trucks, that gives us a profit of $90. So clearly much better. Now looking at that combination, 30 cars and 40 trucks, that gives us quite a bit more money than if we only sold trucks. And then our last vertex is if we sell 50 cars, which could end up being what gives us the most profit overall, because cars give us the most profit, but we end up being a little bit shy. And the reason that is the case is that we don't utilize all of the wheels and seats that we have available. That's what this vertex right here is representing. It is on both of our constraints with wheels and seats. That tells us that we use up every single item that we have each day to make our cars and toys. Okay. Now, when we only sell cars, we end up with extra materials that we don't end up selling because we don't get the right combination to make as many as we can. Okay, so that's why we have a slightly higher profit here with this combination of 30 cars and 40 trucks. So that's our recommendation. You're going to make the most money selling 30 cars and 40 trucks. And again, that makes sense because it is the only vertex from our feasible region that utilizes all of our materials in both constraints.